Okay, grade 9. So this is still the week of January 4th to the 11th. This is topic 1, part 2, or outcome 1, part 2. So we looked at frame of reference, and we know based on frame of reference, we could describe motion. So if I'm driving in the car with Mrs. Tierra and we're going 100 kilometers per hour towards Strathmore, my velocity relative to the ground is 100 kilometers per hour towards Strathmore. My velocity relative to Mrs. Tierra, though, is 0, right? Because relative to her, I'm not moving. Likewise, if my dog was in the car and I'm driving 100 kilometers per hour north towards Strathmore, and my dog jumps from the back seat to the front seat, and he could jump at 10 kilometers per hour, for a little while, he's going 110 kilometers per hour towards Strathmore relative to the ground, but he's going 10 kilometers per hour towards me from my frame of reference. And then when he gets to the front, if he decides to jump back into the back of the car, I'm still going 100 kilometers per hour towards Strathmore. The dog is moving 10 kilometers per hour away from me relative to my frame of reference, but compared to the ground, the dog is now going 90 kilometers per hour, but he's still moving towards Strathmore because the car is going faster than he could jump. Just a review of what we did yesterday. And I guess I'll find out if I embedded some videos in there if they're allowed, or if YouTube won't allow them. So today we're looking at sky coordinates. Okay, so if I said I saw something in the sky, you'd say, where did you see it in the sky? I'd say, over there. And you say, well, I can't see you, I'm on the phone. Where's over there? So what we need is a better way of using language than that. And so we use altitude azimuth coordinates. Okay, and so azimuth, so in order to determine the location of celestial objects in the sky, they need two coordinates measured in degrees called altitude and azimuth. Now, azimuth is an angle measured clockwise from the north. So it could go from 0 to 360. North is 0, right? East is 90, south is 180, west is 270. Back to north again is 360. So 0 and 360 are the same. Altitude, it could be flat with the horizon, which is 0 degrees, or it could be all the way up to straight overhead, which is 90 degrees. So if you put together altitude and azimuth, you can actually describe to somebody where something is in the sky other than saying over there. And using altitude azimuth coordinates, surveyors of the past and present today use it to locate objects in the sky. If you have maybe you have a parent or a grandparent, or maybe you yourself have a fancy telescope, it has altitude and azimuth coordinates on it. Some of the new ones are electronic. You could just type into your computer what altitude or azimuth, or push the button and set it digitally, and it'll go there. Because it's a little bit hard to aim telescopes if you're looking at for one specific thing, but that makes life easier. Once again, it's a lot of money. I have a $9.99 special from Walmart, which I can use to look at the moon. If I sneeze, all of a sudden I'm looking at my garage. So it doesn't work all that well. A device used to measure altitude is called an astrolabe, and here's a picture of it. At its simplest, all it is it's a ruler with a string hanging down. You attach a bolt and put a protractor on it, and you just measure how high in the sky it is. 90 degrees straight up, 0 degrees is flat along the horizon. To measure your azimuth, you need a compass. What, Mr. Chair, the compass that we use for camping? Absolutely, that just tells you what direction to look at. Now, this picture is on page 359 in your textbook. I got one here. Okay, and so we're going to have a look at this. Let me grab my pen. So, let's identify these stars. So here you can see, if you do altitude azimuth, essentially there's a dome around you that you're able to see. And so, I don't know what color, I'll try pink. Okay, and so first one says it's straight west and 40 degrees above the horizon. So you start flat and you go around until you hit, there's straight west. Or if you want, you can go from the center, straight west, and then it's 40 degrees up. Like up here is 90, this is 0, that's about 2/3, that's about at the top, 2/3 around 60, and then 90 degrees at the top. So if you do this and you go up, there it is. That's A. Go with a different color. It's in the southeast, and it's 10 degrees above the horizon. Well, here's south, there's east, so somewhere between here and here, and it's 10 degrees up. Oh, I see it right away. That's east. And then red, maybe. It's straight north and 53 degrees up. Well, straight north is right there. Straight north, 53 degrees up. Let's see. Try a couple more. So we're going to draw where these ones are. Altitude is 70 and azimuth is 290. What color should I use for this one? Ooh, I never use pen. Okay, so 290. So starting here, you're going all the way around. 290 is probably somewhere about there, roughly. And then it's 70 degrees up, so it's almost all the way up to the top. There it is. That's B. Well, B is actually where X is. And then Y azimuth is 20, so it's 20 degrees up, 20 degrees, and altitude is 30. So let's go with a different color. Let's go gray. So my azimuth is 20, so there's 0. So 20 is probably just about here, not very far. Altitude is 30, so from the back side, about a third up, and that's where Y would be. Okay, and at this point in time, there is a worksheet for you to do on page 6 in your notes. Okay, so go to page 6 in your notes. This assignment should take you 5 minutes. So I'm just going to I'm going to go ahead and go and put my note here. Do page 6 that are in your notes. It should take you 5 minutes. So my plan is for these worksheets that you're doing at home, once you are back at school on the 11th, we would go ahead and mark those. Okay, so that's worth 8 marks. 4 marks for the top of the page, 4 marks for the bottom of the page. Okay, and so I would pause for 5 minutes. What I'll do is you pause and I'll just do 5 minutes less in my video. By the way, here's Star Trek, right, where they use altitude, azimuth, coordinates. So when you hear their bearings and their mark, that's what they're talking about. And it's, of course, 3-dimensional as well. So you have altitude and azimuth, and then also how far forward you moved in time as well. So why did we do frame of reference? Because when we look up in the sky, we use the stars as our frame of reference, right? It looks like the stars and planets are turning above us, but they're not. We know it's because the Earth is actually turning. However, if you want to find out what an object is actually doing, you need to use a frame of reference. You can't use the sun. The sun moves quite a bit, and the moon does as well, and the planets are moving. However, the stars are a good fixed frame of reference. Are they moving? Absolutely they are. However, in 10,000 years, to our eye, they'll shift maybe 1 millimeter in 10,000 years. So we can consider them to be a good frame of reference because they don't change very much. Now, why do they not look like they're changing? Because they're so far away. It's kind of like if you stand beside a highway and a car goes by you, it feels like it's going really fast. But if you were 5 kilometers away and you saw the car moving on the highway, it wouldn't look like it's moving so quick because it's so far away. Now, what if you were, 100 light years away from something? It would look like it doesn't change. Like 100 light years means that light traveling at the speed of light would take 100 years to get here, right? And when we're looking at stuff in the background, some of them are millions of light years away. They might not even exist. They might have blown up 6 million years ago. We're still seeing the light from what was being given off from earlier in time. It messes with your head if you think about it too much. So if you want to track Mars, you record its position relative to the stars, okay? And Kepler? Oh, I'm getting old. There was a guy, Kepler, I believe, who made these star charts for for this exact purpose. It's still used today. All right, here is the Earth-centered model. The Earth-centered model has the Earth at the center of the model. Okay, it's also called the geocentric. I mean, think of the word geo, right? Geo, like geology, the study of Earth. The geocentric model puts the Earth at the center. Okay, it's based on Aristotle's ideas that this model dominated thinking for 2,000 years. It's not true. The Earth is not the center of our solar system. However, for the time, that model worked quite well. It was based on math and geometry of Pythagoras and Euclid. He placed the stars on the outer sphere that he termed the firmament of fixed stars or celestial sphere. That's basically the background of stars that don't move. The Earth-centered model, it worked well. Just so you know, it worked. It was able to make predictions of dates and times when celestial bodies rose and set. They were able to predict the seasons with it as well. There was a problem with this model. It needed 55 different inner spheres to work. And for a while, 3 planets, Mars, Jupiter, and Saturn, had to sometimes reverse their direction. We know today there's no way that Mars, Jupiter, and Saturn could turn around and flow the other way, but for their time, this was a decent model, and it fit with church as well, because church said, you know, God created the earth, and the earth is the center of the universe. Therefore, it makes sense that all the heavens would turn above the earth. Okay, and so there's that model, and of course, air, fire, water, and earth, part of the old way of thinking. Okay, good model, though, just not correct. Ptolemy comes along and modifies his model by saying the planets do another thing, is that they spiral as they move around. Okay? And so what you end up with is you end up with the planets moving around the Earth, according to him, but the planets also spiraling like this as they went along. So what happens if you take the motion of a circle and you put a spiral onto it? You get an oval shape, which, by the way, is the shape that the planets are moving around the sun, not the Earth. So the epicycle, Ptolemy's idea, try to keep a model that in play that really was over. I see when I draw it like that, it looks like a sperm. Oval shape. Now, the sun-centered model was proposed by Nicholas Copernicus in the 1500s. And he said the sun was fixed and the planets revolved around it. This is known as the sun-centered or heliocentric model. Now, it's not the reason, but the sun is made of helium. So if you remember, you know the sun is made of helium, it's easier to remember that the heliocentric model has the sun at the center of it. Okay? This was a good model, and he was only able to propose it. He couldn't prove it. The guy who proved it, they locked him up for the rest of his life till the day he died. We're talking about Galileo. He just proposed it. Now, he did not have proof. So what happened? If you propose something totally crazy like this idea, the sun is center, and that was, by the way, totally crazy for the time, because by doing that, you're speaking against the church, and during the Spanish Inquisition, people who spoke against the church could be tied up in the center of town and lit on fire. And so, in this case, because he could not prove it, lucky for him, they just made fun of him. And so people would say, according to you then, what makes day and night? Because the old model is perfect. Day and night is caused by the sun going around the earth. He said, well, I think the earth is turning. They said, you think the earth is turning that fast? It would be windy from the same direction all the time, and people would be going flying off into space. Oh, poor Copernicus, you are such a fool. Lucky for him, though, he couldn't prove it. If he did, they probably would have killed him. Okay, and of course, it went against religion, so that's a big one. To go against religion, you don't want to be doing that. I'm going to try and show another video of the known universe. A student showed me this at one point in time. It's one of my favorites of all time, so I'm going to show it to you. And I don't know if YouTube is going to allow me to do this or not, but we'll try. And then the next thing we're doing is we're doing topic 1 questions, page 365, numbers 1 to 6. But this is the entire universe that we've seen and we've mapped out so far. So here we go. So that definitely puts it into perspective for you. And so at this point in time, you would stop and you would do page 365, numbers 1 to 6. So you have 2 small assignments plus this one that will be due when we come back. I will send out a link for the adapted assignment. My adapted students would not do this. You're doing this. Okay. You're doing that. Adapted students will get email. Okay, and so that should be enough work to keep you entertained for that January 4th till 11th. And I really hope that I'm going to see you right away tomorrow. Well, Monday the 11th. Take care, guys. Bye-bye.